So all right, so with today's class and also Thursday's lecture, you'll be able to build your own digital device. Okay, this lab 2 is modeling something called a ripple carry pattern. Okay, which is binary addition. So you'll be able to do that, after Thursday's lecture. So today you'll be able to start that lab, and there's some preliminary type information that you need to know about before you can actually build that ripple carry out of it. So the agenda is up here. There's 2 dates that we haven't talked about yet that are important. One's called the exclusive ORs or exclusive NOR. So remember, we talked about different dates in the text. I put a handout that has basic dates along with the Boolean expressions that's been on the table there several lectures now. You may recall on that handout, there's 3 of the 5 we talked about, right? Because there's the NOT gate, like the inverter where the output power is the input. And then also the AND and the OR are on there. But the 2 that aren't on there that we also talked about are the NOR and the NAND. Okay. So those 5 gates together, those are what are called the basic gates. And then the exclusive OR and exclusive NOR, those are called compound gates because those gates are made out of the basic gates. Like for example, I believe the exclusive OR is made out of like, right, it's like a NAND gate, an OR gate, and NAND. All the time, same thing with exclusive NOR. It's made out of several of the basic gates. So after we go over exclusive OR and exclusive NOR, then we're going to talk about bit addition, which is going to lead to something called a half adder. And then we'll talk about adding multi-bits, getting more than 1 bit. And that leads to something called a full adder. And then you'll be able to do the activity today. And the activity today is basically prep work for the first part of lab 2. Part 1 is using what we talked about today about the half adder and full adder and actually building, designing each of those in half adder using system parallel. Okay, so that's sort of what the plan is. So we're going to start with the exclusive OR. So here is just like the other dates. Exclusive OR, it's 2 tables looks like this. On if you compare this truth table to the previous truth tables, you can see that this is unique truth table. That's why I have it on logic. If not, what will be the other gates that we talked about? Now, the Boolean expression. Now, the short game. think that's. The door, right? The door is if not exclude the door. The exclude the door, gonna have the same table to people to convert. Exclude the door is equal to an exclusive or with an inverter on the output. It's the same idea as, NOR and an output. Because these are exclusive. So the truth table for the exclusive door is just the opposite of the exclusive door. So the exclusive door, you only get a 1 out. The inputs are the same. When you get a 0 out, you have the Boolean expression for F would just be not E or A B. And shortening similar to how you would do it more. It's just a parallel. Okay. So, any question at this point? See that in the activity today, also for lab 2, it's going to be one of these. You're going to need to know this for what's coming up in the activity and also lab 2. Say that again. That's a semicolon. It's supposed to be a semicolon. Let me get small. Yeah, but remember, it's system parallel, you gotta end the line with a semicolon. So remember, that's just the system parallel way of writing it. Yeah, but thanks for pointing that out. Because yeah, I mean, semicolons kind of like the other thing we're gonna do is we're gonna go over the KMAP example because it ties into gotta write an expression for F. So this is the one. So did we group any of these ones? Make groups that are diagonal in KMAP. What's the only shapes you can have for your groups in a KMAP? Yeah, squares or rectangles. No type like that. So yeah, we cannot do diagonal. So we can't do it. So these are just going to be single groups. That's all we can do. So now I'm going to write the expression where each one variable term, it's going to be the cell, I'm going to get the term A, B, not C, right? That's 0. I'll get the term to be a binary 3, right? So it's not A, B, C. The 5 cell give me the binary of the 5, so it'll be what? A, not B, C. 6 B, A, B. I how to get this right. Binary, the cell number, right? Index is we call the cell numbers indexes. But when you have something like this, we can do further reduction by using the laws and identities, because just like in base 10 algebra, in base 2 algebra, you can factor out common terms. So like right here, I can factor out the not A. So I can write these terms here, the not A, not B, not C, and then or I'm just taking those two terms, I'm just taking the not A outside. And likewise, these two terms here, I can factor out the A. So I can write it as A, and C, or B. Okay, so everybody's doing it right, just like in base 10, right? Now, look. What is that's inside the parentheses? That's an explicit more, right? It's the right here. I mean, this is EV, this is one way. So I can write this as an explicit or. This here. Sorry. Sorry. Where it's more in the now, how about here? It's more with beans. Everybody agree with that? Even go one step further, unless x, and then we have a dummy variable, I let x equal the x that's going to c, I could write it substituting x in for b for the c. And then what do I have here? I can explicit or with a x, right? So then I can make this here, so this is right. Using the dummy variable is, optional, right? I mean, I just use it because for some people it's easier to save to make the substitution. Some people don't need it, right? Some people can go right from here to here. But very well just some people. That's an example of sometimes you can do additional reduction if you have either one of these forms. And when you have single groupings that are diagonal from each other, like we have here, usually that's the case. I can say 100%. I can say most of the time you have single groupings that are diagonal from each other. You can probably get an exclusive or an exclusive non-active. You're going to see that in your activity, you're going to have a K-map that's similar to this. And you're going to have to do something very much like not exactly the same thing, but very, very similar. So we need questions up to this point.
With yeah, Yeah, you have to keep the parentheses, like the order of operations work out.
Yeah, you go.
Okay.
Yeah, yeah, like sometimes you don't see it written like this. Parentheses would be like that, but you don't need the parentheses, this could be a different order. Yeah, so yeah, order doesn't matter in base two, just like in base 10. That's a good point, thanks. Any other questions? Next thing we're gonna do is, we're gonna look at single bit addition, right? Because just like in being 10, right, you can do addition well in base two, you can do addition. And we're gonna start out with the rules of single bit addition. So 0 plus 0. 1 plus 1 is 2. Now, how do you write 2 in binary? So next time you're talking to your parents or got somebody paying for your school, you can tell them that in your third quarter freshman college class, you learned that 0 plus 0, 0 plus 1, 1 plus 0, 1 plus 1 is equal to. I'm sure they'll be very proud of where their money is going. Okay, but the next thing we're going to do is we're going to take these rules of single bit binary addition and we're going to put them into a truth table. And you see, if we put anything into a truth table, we can then get a logic circle for it. And that's one of the things we learned what the second class looked like, right? There's the different forms that you can represent logic expressions, right? There's truth table, expressions, logic diagrams, right, with the gates and so on. So, because then we can get an expression from it, a Boolean expression, and then you'll be able to model it in your system on the bottom. Now, to put it into a truth table, we're going to define some variables. I'm going to call this top row A, bottom row B. Least significant bit, most significant bit, right? Least significant bit is the bit furthest to the right, most significant furthest to the left. Okay, well, this least significant bit of the result, we're going to leave with S. It's these bits that we're adding that we labeled A and B. These are going to be inputs. Okay, so let's make the truth table. Remember, on the left side, but A and B on the left, and output on the right side, so C that. Okay, so now I'm just going to take each rule and put it into the truth table. So when A and B are both 0, C and S are both 0. When A is 0 and B is 1, C is 0, S is 0. When A is 1 and B is 0, C is 0 and S is 1. And when both A and B are 1, C is 1, S is 0. Okay. Or like I just took these rules after I gave each row and each result into the variable, and I just put them into the truth table. So now from the truth table, we can get Boolean expressions. You can also put this into a K-map, right? Just like you can put an 8-row truth table into an 8-cell K-map and a 16-cell, or excuse me, a 16-row truth table into a 16-cell K-map. You can put a 4-row table into a 4-cell K-map. Now, most of the time, people don't do that because when you have just 4 rows in your truth table, you can get the expression for each output by just looking at each output separately and how it compares to the input. For example, if you block out output S and you just look at how output C relates to the inputs, can you see what kind of gate that is? C is only a 1 when both inputs are 1. Okay. You see what kind of gate S means if you just look at the S output, you compare it to the input. So S is only a 1 when the inputs are different. It's 0 when they're the same. Yeah, we just talked about it. Okay. So, when you have a truth table that's only 4 rows, it's not really necessary to go into K-map. Now, I'll write what the K-map would look like, just because you haven't seen a 4-cell mechanic, but like I said, most people never use a 4-cell. But a 4-cell K-map is just like this. It's just got 4 cells, this is 0, this is 1, this is 2, this is 3, this is 8. Okay. From this truth table, which you're going to do the lab 2. How about that? People came from these rules of this addition. So what that means is the half adder is performing these rules of single bit addition. And one of the things that you're asked to do as part of the activity is make a black box diagram of a half adder. Black box diagram shows. It just shows outputs, right? So you're just going to have 2 inputs, right? Your A, B, 2 outputs, your C and S. And then give it a name. Call it half adder, or call it feature, give it a name. You always give your black box diagram a name in addition to identifying the outputs. That's part of the activity. So, any questions up to this point? Everybody's good? Okay, the next thing, turn the camera. Don't forget the times. The next thing is to look at multi-bit addition, because often when you're doing any sort of addition that's useful, it's more than a single bit. Useful addition in binary is usually multi-bit. Like here, we're adding 2 4-bit binary numbers. The least significant bits here are the 1s column, right? The 2s, the 4s, the 8s. So this 0, 1, 1, 0. What is this equal to in base 10? 6. Today 0, 1, 1, 1. We see here we're just adding 6 plus 7 in binary. And when you add in binary, when you're adding multi-bit numbers in binary, you add them the same way when you're adding multi-digit base 10 numbers, right? You start with the least significant column, you add that column, and you may have a carry, right? And if you have a carry, you include that in the next column and so on, right? Same sort of thing here. See, we start with the least significant bit column. We're adding 0 plus 1, so that's 1 with no carry. Carry of 0, if you will. Then we have 0 plus 1 plus 1, which is 2. We did 0 with a carry of 1. And now we have 1 plus 1 plus 1, which is what? 3, which is going to be a 1 with a carry 1. Well, 1 plus 1 plus 1, the half adder cannot do that addition. Because the half adder only has 2 inputs. And to add 1 plus 1 plus 1, you need 3 inputs. So you see the half adder while it will perform these roles, it has a limitation. The limitation is that in multi-bit addition, you could run into a case where you need to add 3 bits and the half adder can only add 2 bits. So it can't handle that third bit. Okay. Be a one to carry on that 1 plus 0 is 0. Let's see if we get it right. This answer. 1101 is that. So because the half adder cannot handle a third input, there's this other adder that's called a full adder. And the full adder has this truth. It has 3 inputs. Also has 2 outputs, but one output is labeled C0 and the other X. Can you guess what the CI stands for? Or carry in or carry out. Okay. Now, since the full adder has 3 bits at the input, right? 3 inputs that can either be 0 or 1. How many unique combinations can I get with 3 bits? How many? 8. So again, that goes back to this. Zero, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0. See, any significant bit, right, in your binary, it's going to change every time. Say, look, 0, 1, 0, 1, 0, 1, 0, 1, you know, we kept going, do the same thing, 0, 1, 0, 1. And then the next bit changes every 2. So you see here 0, 0, and then goes 1, 1, and 0, 0, 1, 1, and that would just continue on forever. And the next bit is changing before, see that 0, 0, 0, 0, and then 1, 1, 1, 1. You know, if we had another bit over here, it would be like 8, 0, and then 8, 1, and just keep repeating. So there's always these patterns when you're dealing with, you know, binary numbers. Okay. All right. So now at the output, we're just adding these 3 bits. Right. So of course, if all the bits are 0, the result is 0. Then any row where I have just 1 bit equal to a 1, well, the result's going to be 1. So 0 plus 0 plus 1 is just going to be a result of 1, which is the carry out of 0 that's on 1. We'll get the same thing here. Break this one for the time. Here we have another row with just one that they're adding. So that would be 0, 1. Then the rows that have 2, 1, the result is going to be 2, which is 1, 0 binary. So the carry out would be 1, and the sum would be 0 for those rows. Right? So 1, 0, 1, 0. And then here we get a row where all 3 bits are 1. So that's when the result is 3, which is 1, 1. So everybody see how I filled out the outputs and just adding the 3 bits. Okay. So what we're going to do as part of the activity is now take this truth table for the full adder and come up with the reduced expression for carry out and also sum. Now, this is the first time the half adder and the full adder. This is the first time you've had a truth table with more than one output, I'm pretty sure, right? So all the other truth tables, it's just been one output. Let's be true for all the key maps. Anything came out with different people, just have one output. Okay, when you have more than one output for a truth table, that means you're going to have more than one K-map because each output has its own K-map. Okay, so you're going to have an 8-cell K-map, you know, for S. And then you're going to have a whole another 8-cell K-map that's separate for C here. each output has its own K map. You never see a K map that has multiple outputs. Because remember, what goes in the cells of the K map is the output value. And it would make sense to have two output values inside the same cell. Okay. So part of the activity is making the K map for output S, making the K map for output carry out, and then coming up with the reduced Boolean expressions for both. Okay, so you're going to have a Boolean expression for S. You'll have something S equals the Boolean for the reduced equation. Then you'll have another equation for this K map for C0. Likewise, with the half averages, looking at the truth table, like we talked about, you'll have an equation for C, you have an equation for S. So you're going to have four equations, right? Two for the half adder, two for the full adder. One of these equations for the full adder, you know, something like this. If you're going to see that with one of those K maps, you're going to have ones that are diagonal, single group. So you're going to have to do pretty similar to what I did here. Exactly the same, but similar. Okay, so do you have any questions up to this point? What's left to do is I just want to show you the activity on Canvas and then talk about the first part of that, to just make some additional comments about that, and then you'll be ready to work on the activity, and then after that, start on the lab. Very similar to last week, that if you're able to get to a certain point in the lab by the end of class day, or at the very latest, the beginning of Thursday, say, at the beginning of Thursday's class, you can get to this point. You'll only have to do like one additional thing on Thursday. You'll be in good shape to finish lab 2 on Thursday. And I'll be more specific there coming up. But okay, before I put the screen down, everybody's good up to this point. It's all making sense. Okay. This is the activity for today, and I've done some of it for you. I want to draw the black box diagram both for the half adder and full adder. Right? So again, black box diagram just shows us the main input, main output, also given a name. So we'll have two black box diagrams, one for the half adder, one for the full adder. Truth tables, you already have the truth tables. I have them up on the board, but actually write them out. It might be turning. I know you're just copying what I have, but just to make sure, as you're writing them, make sure you understand them, right? That they make sense to you. Okay, K-map. I'm only requiring a K-map for both the S and the carry out for the full adder. Like I said, the K-map's not really necessary for the half adder. I mean, if you want to show it, that's fine, but I won't take off points if you don't include the K-map. But do include the truth table and show what expressions you get from the truth table. And then also show the expressions that you get from the K-map for the full adder. Okay. So again, there's going to be 4 equations. Right? The half adder has 2 equations. The full adder has 2 equations. Okay. So really, the activity this week is just prep work that you have to do for the first part of lab 2. You would have to do this anyway to do the first part of the lab. Okay. So any questions on the activity before I put the screen back up and make a few more comments? Well, actually, before I do that, let me show it's actually part of the lab. It's this step of the lab. Okay, and then after you're done with the activity, that's when you now go to Bovado. This is where I want to do. I want to show something from the whiteboard. So, any questions for the screen? I'm really trying to protect your eye. I'm trying to protect off this button run. Is that this week there's going to be 2 design sources and 2 sim files within the same project. Okay, so you got one project, but in your source window, the source window it shows your design sources, right? Your sim file. Well, you're going to have 2 design sources. But maybe you label or you name your half adder file, HJ. Or you like HJ, that's the system parallel, you can say FA for full adder, FT system parallel. And this design source for the half adder is going to have these 2 equations that you come up with. This full adder design source file is going to have these 2 equations that you come up with. Okay, likewise, you're going to have a test pitch. Essentially, top pattern. It's all in the same file. Now, I don't know if you've noticed, but in the bottom, next to the left of the file name, you'll see this like pyramid. It's like a pyramid. People see that. Indicates so you have multiple designs and multiple zip files. Whenever you go to simulate, I want to simulate the half adder. I'm going to make sure that the half adder design source is the top module, and I also have to make sure the half adder sim file has been developed as the top module. Okay, so if you have this, when you go to run the sim, it's kind of sim and a half adder. And then if you make the full adder top module, and the sim file for the full adder top module, it will run that simulation. And the way you make a file the top module is you just right click on it, and then you come up and there'll be an option to set the time. Okay. A common error is, somebody will want to simulate the full adder, and they have the full adder design source as the top module, but then we still have the half adder sim file as the top module, and now it's not going to sim what you want it to sim. Right? Because the half adder is going to have different test cases than the full adder. Because the half adder, how many test cases do you need to verify that your half adder works? Right, 4, because there's 4 rows in the truth table. How many test cases do you need for the full adder to test it? 8, because there's 8 rows in the truth table. Okay, so they got different test cases. Okay. The other thing I want to mention is that you do not need a constraints file at this point. You will need a constraints file after Thursday's class. But for today, if you can get a successful simulation for your half adder and a successful simulation for your full adder, then on Thursday, after the lecture on Thursday, you'll only have to add one additional file in order to complete lab 2. Okay, because on Thursday, you're going to learn something called structural modeling. And we're also going to talk about how, just like we add column by column when we do manual binary addition, the hardware, this thing called a ripple carry adder, it also does the addition column by column. So you're gonna need an adder for this column, an adder for this column, an adder for this column, an adder for this column. You're essentially gonna need 4 adders to add these 2 4-bit binary numbers. And the way we'll accomplish it, as you'll see on Thursday, is by doing something called structural modeling, which will require 1 additional file to these in order to, get it to add multiple 4-bit numbers like this example. Okay, so like I said, key thing. Okay, right here. And also, don't worry about a constraint yet for this. Okay, you won't need it till Thursday. You're not downloading anything today. You're just simulating the half adder and simulating the full adder. Okay, so do you have any questions before you get going? Because you have enough information now to do the activity. And I have the answers to the activity up here. And then once you're done with the activity, you can start working on the lab. Again, I want to remind everybody to get credit for the activity. You do have to be physically present for that, right? So don't leave until your cable turns in the activity. So to make sure you get credit. And then after that, once you start the lab, then it's optional if you want to stay in the room. If you want to go somewhere else and do the lab, that's fine with me. Okay, everybody's good? And Ethan will be here in an hour or so to help out.